today. Okay, we started that yesterday. And so let's just remind ourselves what L'Hopital's rule is in a nutshell. We have the limit as x approaches a of f of x over g of x. Okay. And this limit has to be of indeterminate form, right? When you do the direct substitution, you have to end up with 0 over 0 or infinity over infinity. Okay, it has to be one of those indeterminate forms. Okay? Just leave it there.
Enjoying the weather.
Well, I took attendance. I counted you absent.
Oh,
Now I gotta go back and uncheck you. Okay. So if we have the limit as x approaches a of f of x over g of x, right? In indeterminate form, 0 over 0 or infinity over infinity, then L'Hopital's rule says this limit is equal to the limit as x approaches a of f prime of x over g prime of x if the limit exists. Okay. So this limit is equal to this limit if this limit exists. And this limit is of either 0, 0 or infinity over infinity in determinate form. Okay. So we did an example at the end of class yesterday. So let's do another one. Do the limit as x approaches 0 of the square root of 1 plus x minus 1 minus 1/2 x over x squared. Okay. Doesn't look like a lot of fun. But what's the first step in evaluating that limit? Direct substitution, right? So we put 0 in for x. We have square root of 1 plus 0 minus 1 minus 1/2 times 0 over 0 squared. One plus 0 is 1. Square root of 1 is 1. 1 minus 1 is 0. And 1/2 times 0 is 0. So we end up with the numerator is equal to 0. And denominator 0 squared is equal to 0. So we have 0 over 0 form. Okay? Indeterminate form. So we can apply L'Hopital's rule in evaluating this limit. Now we might be able to use algebra. Remember at the beginning of the semester, exam 1, you had to use algebra to evaluate certain limits, but L'Hopital's rule might make it a lot faster. Okay. So before we apply L'Hopital's rule, we got to rewrite the numerator. Square root of 1 plus x is 1 plus x to the 1/2. And now we can apply L'Hopital's rule. Okay. And I put LR above the equal sign to indicate I'm applying L'Hopital's rule. And we have the limit as x approaches 0. Now I differentiate the numerator, right? So the derivative, right? We differentiate the numerator and the denominator with respect to x. So derivative 1 plus x to the 1/2. You bring the 1/2 down, right? We're doing general power rule. Times 1 plus x. Subtract 1 from the exponent. And then the derivative of what's inside parentheses, the derivative of 1 plus x is just 1, right? So that's the derivative of 1 plus x to the 1/2. The derivative of constant minus 1 is 0. And the derivative of minus 1/2 x with respect to x is minus 1/2. In the denominator, the derivative of x squared is 2x. Well, now we can do the direct substitution. So I put 0 in for x. I have 1/2 times 1 plus 0 to the minus 1/2 minus 1/2 over 2x. Okay. So in evaluating the numerator, you got to do PEMDAS, right? 1 plus 0 is 1. 1 raised to any power is 1, right? So 1 to the minus 1/2 is 1. 1 times 1/2 is 1/2, and 1/2 minus 1/2 is 0. So the numerator is equal to 0. Oh, the denominator, I'm putting in 0 in for x. Okay, I forgot to do that. The denominator, we had 2 times 0, which is 0. So again, we're 0 over 0 form. Okay. Well, guess what? We can apply L'Hopital's rule to this limit. Okay. So this is equal to the limit as x approaches 0. So if this limit exists, it's equal to this limit, which is equal to this limit, okay, our original limit. Okay. So differentiate the numerator, okay? Derivative of 1/2 times 1 plus x to the minus 1/2 by general power rule. Bring the minus 1/2 down front. Minus 1/2 times 1/2 is minus 1/4. And times 1 plus x. And then we subtract 1 from the exponent. Minus 1/2 minus 1 is minus 3/2. And then times that by the derivative of what's inside parentheses, and the derivative of 1 plus x is just 1. In the denominator, the derivative of 2x is 2. So now I can do the direct substitution. I put 0 in for x. I have minus 1/4 times 1 plus 0 to the minus 3/2 over 2. All right, we're not going to end up with 0 over 0, right? So 1 plus 0, right? You got to do PEMDAS. 1 plus 0 is 1. 1 raised to the minus 3/2 is 1. Minus 1/4 times 1 is minus 1/4. Divided by 2. Remember, when you're doing division with fractions, right? It's keep, switch, flip. And when you do the keep, switch to multiplication, flip the 2, you end up with minus 1/8. So this limit that we started with, the limit as x approaches 0 of this function, is equal to minus 1/8. Are you guys in front having a hard time seeing this answer? Can you see it? Can you see it? Can you see it?
No.
What can you see?
I can see now. By like you.
The minus 1/8? Okay. So I'll try not to use this side of the board, okay? Any questions on it? Okay, so for this function, the limit as x approaches 0, right, is equal to minus 1/8. This function is undefined at x equals 0. We showed that right here, okay? But the limit still exists, okay? All right. No questions? So you can apply, in evaluating limit, you can apply L'Hopital's rule more than once, right? We applied it here, okay? This is 0 over 0 form. And then we applied it again, because when we do the direct substitution, we get 0 over 0 form again, right? So you can apply L'Hopital, keep applying L'Hopital's rule until you evaluate the limit, okay? All right. So next, let's take a look at the limit as x approaches 0 of sine x over x. So when you do the direct substitution, we have the sine of 0 over 0. And remember, right, x going into the sine function is radian measure. Okay. Remember, radians can be treated as real numbers. Okay, it's not degrees. So what's the sine of 0 radians equal to? Anybody know? Trigonometry? Unit circle? Anybody? Now, Eric should know. And say what? It's 0. Okay. So sine of 0 radians, same as sine of 0 degrees, is equal to 0. Right? So we get 0 over 0 form. So we can apply L'Hopital's rule. And the derivative of cosine x, or derivative of sine x, is cosine x. The derivative of x with respect to x is just 1. So this is equal to limit as x approaches. This limit is equal to limit as x approaches 0 of cosine x over 1. And now we do the direct substitution. Cosine x divided by 1 is just cosine x. And the limit as x approaches 0 of cosine x is cosine 0. And cosine 0 radian is equal to 1. So this function, sine x over x, is undefined at x equals 0, but the limit still exists. Okay. All right, next we have the limit as x approaches 1, natural log of x over x minus 1. So when you do the direct substitution, we have the natural log of 1 over 1 minus 1. And you should know that the log of 1 in any base is equal to 0. And 1 minus 1 is equal to 0. So this function is undefined at x equals 1, but the limit still exists. Okay. So using L'Hopital's rule, the derivative of the natural log of x is 1 over x, and the derivative of x minus 1 with respect to x is just 1. So this limit, 1 over x divided by 1, is just 1 over x. And when you do the direct substitution, you get 1 over 1, which is equal to 1. So this function is undefined at x equals 1, but the limit as x approaches 1 of this function is equal to plus 1. Okay. All right, any questions on that? Okay. All right. Let's do one involving infinity. So we have the limit as x increases without bound of e to the x over x squared. So let's just remind ourselves what the natural exponential function looks like. This is the graph of y equals e to the x. So you can see as x increases without bound, the value of e to the x increases without bound. Okay. And then let's remind ourselves what the graph of x squared looks like. That's a parabola. It goes through the origin. And you can see that as the variable x increases without bound, the value of the parabola, right? The value of x squared increases without bound. Okay. So we can write the limit as x increases without bound of e to the x, it's not e to the x, is infinity, right? So this limit doesn't actually exist, if you recall from our study of limits, but we write plus infinity to indicate the behavior. Okay. And then the limit, right, this is review from, I think, example 1, or from exam 1, right, and review is always good. And so the limit as x increases without bound of x squared, right, is infinity. So, this, as x increases without bound, the numerator increases without bound, the denominator increases without bound, and so we have infinity over infinity form, indeterminate form. And we can apply L'Hopital's rule. Okay. So, we differentiate the numerator and the denominator. The derivative e to the x is e to the x. The derivative of x squared is 2x, right? Well, as x increases without bound, e to the x in the numerator increases without bound. And as x increases without bound, 2 times x increases without bound, right? You're doubling. X is increasing without bound, and so when you double it, right, it increases without bound twice as fast. Okay. So we have infinity over infinity form. Okay. And so in evaluating this limit, we can apply L'Hopital's rule. So we have the limit as x increases without bound. The derivative of e to the x is e to the x, and the derivative of 2x with respect to x is 2. So as x increases without bound, e to the x increases without bound, and we can write infinity, right, to represent that. As x increases without bound, e to the x is increasing without bound. The denominator stuck at 2, and infinity divided by 2, 1/2 of infinity is still infinity. Okay. So, technically speaking, this limit does not exist, but we write infinity to indicate in the graph of that function in the coordinate plane, right, the right end is going up forever. Okay. The larger the value of x, the larger the value of y. Okay. Any questions on that? So as x increases without bound, e to the x over x squared increases without bound. Okay. All right. Now let's take a look at a one-sided limit. So we have the limit as x approaches 0 from the right. Remember the plus sign, the superscript means from the right. So we're looking at values of x greater than 0. Of x times the natural log of x. Well, as x approaches 0 from the right, x here approaches 0, right? As x approaches 0, x approaches 0, okay? So I'm just doing the direct substitution. Okay? Now, remind you of the graph of the natural log function, the natural log of x. Right? It looks something like this. Crossing the x-axis at x equals 1. And remember, the natural log function is the inverse of the natural exponential function. Okay. So as x approaches 0 from the right, the value of the natural log function is decreasing without bound, right? Going to minus infinity. So this is what we call 0 times infinity form. We can't apply L'Hopital's rule the way it's written. Yes, sir. Ma'am. Sorry.
So it doesn't make a difference if it's increasing.
No, it doesn't. Because you could write 0 times minus infinity. It's just 0 times n infinity. Okay. So the way this function is written, we cannot apply L'Hopital's rule, right? L'Hopital's rule requires 0 over 0 form or infinity over infinity form. Okay. Well, fortunately, we can rewrite x times the natural log of x as the natural log of x divided by 1 over x. You can write it as a complex fraction, right? This is the natural log of x divided by 1 over x. Remember, when you do division with fractions, you keep, switch, flip. So you keep the natural log of x, you switch division to multiplication, and then you flip 1 over x to x over 1. X over 1 is x. So you have the natural log of x times x, which is the same as x times the natural log of x when you switch the order of multiplication. Okay? Well, when you do the direct substitution, right, as x approaches 0 from the right, the natural log of x, right, is going to minus infinity. Okay? So we have minus infinity in the numerator, and in the denominator, okay, as x approaches 0 from the right, 1 over x is going to plus infinity. So it doesn't have to be minus infinity over minus infinity or plus infinity over plus infinity. It can be, one can be minus and one can be plus. And so this is infinity over infinity form. So now we can apply L'Hopital's rule. Okay? So we got to differentiate the numerator and the denominator, right? So 1 over x is the same as x to the minus 1 power, right? And so now we can apply L'Hopital's rule. The derivative of the natural log of x with respect to x is 1 over x. And the derivative of x to the minus 1, bring the minus 1, right? Just use the power rule, bring the minus 1 down front, subtract 1 from the exponent. So now we simplify. We have 1 over x divided by x to the minus 2, you know, is 1 over x squared. So the negative of x to the minus 2 is the negative of 1 over x squared. Now, in doing these, dividing these two quotients, right? Keep, switch, flip, right? So we have the limit as x approaches 0 from the right of 1 over x times minus 1 over x squared. I brought the minus sign into the numerator. I can do that, right? The negative of 1 over x squared is the same as the minus 1 over x squared. So keep, switch, oh boy, did I mess that up? Keep, switch, flip. So when you flip the negative of 1 over x squared, you get x squared over 1, right? So x squared over negative 1. And now, by the rules of exponents, x squared, well, let's just multiply straight across. Review is always good. 1 times x squared is x squared, and x times negative 1 is minus x. The rules of exponents, right? This x cancels out one of those x's, and we're just left with a negative x. And now you do the direct substitution, and you have a negative 0. Right, we put 0 in for x, and negative 0 is just 0. So as x approaches 0 from the right, x times the natural log of x approaches 0. Okay. This function is undefined at x equals 0 because the natural log of 0 is undefined. Okay. Any questions on that? So whenever you have a function that's of 0 times infinity form, You gotta manipulate that function to get it into 0 over 0 form or infinity over infinity form before you can apply L'Hopital's rule, okay? Are you with me? It's gotta be in 0 over 0 form or infinity over infinity form before you apply L'Hopital's rule, okay? Alright. Now let's take a look at one that's infinity minus infinity form. So we have the limit as x increases without bound of the natural log of 3x minus 1 minus the natural log of 2x minus 1. So the arguments going into the natural log function in these two cases, if I were to set y equal to 3x minus 1, you would note that y equals 3x minus 1 is the equation of a straight line and with a slope of 3. And so as x increases without bound, okay, 3x minus 1 increases without bound, right? Because further out you go on the x-axis, the larger the value of 3x minus 1 is, right? Because the graph goes up forever, okay? And you know from the graph of the natural log function, which I had up and erased, as x increases without bound, the natural log of x increases without bound. So as 3x minus 1 increases without bound, the natural log of 3x minus 1 increases without bound. Okay, are you with me? Okay. So the limit as x increases without bound of the natural log of 3x minus 1, we say is equal to infinity, right? It increases without bound. And the same is true for the natural log of 2x minus 1. As x increases without bound, 2x minus 1 increases without bound, and the natural log of 2x minus 1 increases without bound. So, this limit is of infinity minus infinity form. Okay? That's not 0 over 0. And that's not infinity over infinity. And in order to use L'Hopital's rule, we got to have 0 over 0 form or infinity over infinity form. Right? We can fix this problem. And the deal is, infinity minus infinity is not 0. It's undefined, right? We actually on exam 1, or before exam, I don't think I had a problem on exam 1, but we did a problem in class where we had to find the limit as x approaches infinity using algebra, okay, of a limit that was infinity minus infinity form, okay. It was very tedious, the algebra, okay. We won't have that problem here, okay. So, this in parentheses, using the rules of logarithms, I can condense this inside the parentheses here, right? Using what rule of logarithms? There are 3 of them, right? Product. Say what?
Isn't it division?
Division, right? The quotient rule. The quotient rule of logarithms says the natural log of A over B is equal to the natural log of A minus the natural log of B. And if you switch the two sides, you have the natural log of A minus the natural log of B is equal to the natural log of A over B. Okay? So this difference in natural logs from the quotient rule can be written as the natural log of 3x minus 1 over 2x minus 1. This is my A, this is my B. Well, from the laws, from the limit laws that we studied at the beginning of the semester, you can bring this, since the natural log function is a continuous function, okay? You can bring the limit inside the natural log, inside the argument of the natural log, and we have the natural log of the limit as x increases without bound of 3x minus 1 over 2x minus 1. Well, most of you probably know what that limit is equal to, right, from our study of rational functions, okay? What's this limit equal to from our study of rational functions? Remember horizontal asymptotes? Okay. This is a polynomial degree 1 in the numerator, polynomial degree 1 in the denominator. What? 3 over 2, very good. Okay. But we're going to apply L'Hopital's rule because that's more fun. So bringing the limit inside the natural log comes from our study of limit laws at the beginning of the semester. I'm sure you've forgotten, right, a lot of that stuff, right? Semester's 15 weeks long, you can't remember everything, okay? But we did study limit laws, right? Well, this limit inside the argument to the natural log function, as x increases without bound, 3x minus 1 increases without bound, 2x minus 1 increases without bound, and so we got infinity over infinity form. We can apply L'Hopital's rule, okay? So this is equal to the natural log, the limit as x increases without bound. The derivative of 3x minus 1 is 3. The derivative with respect to x, and the derivative of 2x minus 1 with respect to x is 2. And the limit of a constant is just the constant. So this is equal to the natural log of 3 halves. And we put 3 halves inside parentheses if you want. So as x, so in this case, infinity minus infinity is not 0. Okay? It's 3 halves. Okay? Actually, right, the natural log of 3x minus 1 goes to infinity, and the natural log of 2x minus 1 goes to infinity. And so in this case, infinity minus infinity is equal to the natural log of 3 halves. So infinity minus infinity is not 0. It can be, but it doesn't have to be. Okay? Any questions on that, ladies and gentlemen? Yes, ma'am.
What is the reason for not taking the derivative of ln? Like, I understand you pulled it out, but you.
So remember, L'Hopital's rule enables you to differentiate the numerator and the denominator. Okay? And so by the limit laws, we were able to take this limit and bring it inside the argument to the natural log function. Okay? It's not, we don't have the natural log of 3x minus 1 over the natural log of 2x minus 1. If that was the case, then we would differentiate the numerator and denominator, and we would differentiate, right, we differentiate the natural log function. Here, we're differentiating the argument into the natural log function. Okay. So far, so good? Okay. All right. Now, one of the things that I wrote on the board yesterday, one of the notes was, let me look it up so I don't say it. L'Hopital's rule never allows us to conclude that the limit as x approaches a of f of x over g of x doesn't exist. So, L'Hopital's rule doesn't allow us to say that limit doesn't exist. Okay? And we're going to demonstrate that with an example. Okay. L'Hopital's rule doesn't always give us an answer. Even when we have 0 over 0 form and infinity over infinity. So when L'Hopital's rule fails to produce an answer. Okay? That's what this example is all about. So we're going to find the limit as x increases without bound of x squared plus 1 over x. Now at the beginning of the semester on exam 1, you had to use algebra to find that limit, right? You divided top and bottom by x. Well, in the numerator, as x increases without bound, from my graphs earlier, we know x squared increases without bound. So x squared plus 1 increases without bound. And so the square root of that increases without bound, right? If I put infinity in for x, I have infinity squared plus 1, right? Infinity squared is infinity. Infinity plus 1 is infinity. Square root of infinity is infinity. And as x increases without bound, x increases without bound, right? As x goes to infinity, this x goes to infinity, right? So, we have up here infinity over infinity form. So we can apply L'Hopital's rule, okay? But before I differentiate the numerator, I got to rewrite the numerator, right? This is equal to the limit as x increases without bound of x squared plus 1 to the 1/2 over x. And now applying L'Hopital's rule, I can differentiate the numerator and the denominator. So differentiating the numerator, use the general power rule, bring down the 1/2 from the left parentheses, subtract 1 from the exponent, 1/2 minus 1 is minus 1/2, and then we gotta multiply that by the derivative of x squared plus 1. Derivative of x squared is 2x. Derivative plus 1 is 0. Now we differentiate the denominator. Derivative of x with respect to x, is 1. Okay. And now we simplify. Okay. So we're dividing by 1, so we can just ignore that. 1/2 times 2 is 1, right? We get rid of that. And then anything raised to the minus sign and exponent means reciprocal, right? So I can bring x squared plus 1 to minus 1/2 down into the denominator. And so we're left with x over x squared plus 1 to the 1/2. You agree? Now, as x increases without bound, x in the numerator increases without bound. And we already know from over here, as x increases without bound, the square root of x squared plus 1, right? This to the 1/2, this is square root of x squared plus 1. That increases without bound. So we have infinity over infinity form. So we can apply L'Hopital's rule, right? So we have the limit as x increases without bound. The derivative of x is 1. And now we differentiate the denominator. Bring the 1/2 down from the left parentheses. Subtract 1 from the exponent. 1/2 minus 1 is minus 1/2. And then multiply that by the derivative of what's inside parentheses. Derivative of x squared is 2x. Derivative of 1 is 0. And now we simplify. Okay? 1/2 times 2 is 1. Okay? And now the minus sign in the exponent, right? When you have this quantity in the denominator, right? That means bring it up to the numerator, right? So over here, the minus sign means reciprocal. Put it down in the denominator. Over here, the minus sign means bring it up and put it in the numerator. Okay? So we have the limit as x increases without bound. X squared plus 1 to the 1/2 over x. There's a problem. You see it? What's the problem, Chance?
It's the original
Yeah,
equation.
we're right back to where we started. So we could just keep going in circles, dog chasing his tail forever. Okay? So we're back to where we started. So that's what it means. You cannot conclude from L'Hopital's rule, right, that if it fails to produce an answer, that this limit does not exist. This limit does exist, right? Using algebra from exam 1, okay? So, review is always a good thing, okay? This is a good question to put on the final exam. So people will spend the whole period trying to apply L'Hopital's rule to it, okay? So the limit as x approaches infinity, square root of x squared plus 1 over x. So this is exam 1 review. You divide, we gotta do algebra, divide top and bottom of the, right, the numerator and denominator by x. But remember, the square root of x squared is equal to x when x is positive, right? X is going to plus infinities. So x is also equal to the square root of x squared when you switch the two sides. So when we divide the numerator by x, we're actually dividing the numerator by x squared. Square root of x squared. Because then we can put this this entire fraction under one radical. Okay. And then in the denominator, we have x over x. Okay. So the numerator, we can put this under one radical. And we have x squared plus 1 divided by x squared, which simplifies to 1 plus 1 over x squared. If I lost you, say something. We can put this fraction under one radical, and then I got to divide x squared into x squared, which is 1, and then x squared into plus 1, which is 1 over x squared. Okay. So x squared over x squared is 1, and then I got plus 1 over x squared. Okay? And the denominator, x over x, is 1. And then the limit laws, you know, you bring the limit in under the square root, right? The square root is a continuous function, blah, blah, blah. 1 over, so as x increases without bound, 1 over x squared goes to what? 0, right? The limit as x increases without bound of 1 over x squared is 0, right? The graph of 1 over x squared for just positive values of x looks like that. The larger the value of x, the closer the value of y is to 0. Okay? So as x increases without bound, and I can ignore the 1 in the denominator, this is equal to 1 plus 0. Okay? As x increases without bound, 1 over x squared goes to 0. So I have square root of 1 plus 0. Square root of 1, which is 1. So, as x, the limit as x increases without bound of this function is actually equal to 1. But L'Hopital's rule won't give us that answer. Okay? We'll just keep going in circles with L'Hopital's rule. Okay? Even though you got infinity over infinity form, L'Hopital's rule won't give you an answer. Okay? Review is good, right? Limit as x increases without bound, 1 over x squared is 0. Okay. Yeah, those are the kinds of things that you always got to remember. Okay. All right. We're almost done with this section. We got 2 more examples. Okay. Can we erase this? See? And so I'll definitely get the homework released this evening, and it'll be due Monday night. And then tomorrow you'll get your next handout on the next section. Okay. All right. So now let's do the limit. As x approaches 0, of tangent x over x. We did earlier sine x over x. Okay. There's a reason I'm doing this. It's for the last example we're going to be doing. So, as x approaches 0, right, this quotient approaches tangent 0 over 0. What's tangent 0 equal to? Does anybody remember? It's equal to 0. So this is 0 over 0 form. So we can apply L'Hopital's rule in evaluating this limit. So this is equal to the limit as x approaches 0. Now we got to differentiate. What's the derivative of tangent x with respect to x? What is it?
Secant squared.
Yeah, secant squared x. And the derivative of x in the denominator, you know, is equal to 1. Okay. Now, riddle me this, ladies and gentlemen. Secant x is the reciprocal of what trig function? It's equal to 1 over what? Cosine x, right? So, as x approaches 0, okay, this equals, we do the direct substitution, secant x squared approaches secant 0 squared, right? So secant 0 is equal to 1 over cosine 0. And what's cosine 0 equal to again? 1. So this is equal to 1 over 1, which is 1. So secant 0 is equal to 1. So secant 0 squared is equal to 1 squared, which is 1. Okay. So as x approaches 0, of tangent x over x, this function's undefined at x equals 0, but the limit as x approaches 0 of tangent x over x is equal to 1. Okay. All right, last example. We need this result for the last example. Okay. We have the limit as x approaches 0 of x minus tangent x over x cubed. So when I do the direct substitution, I have 0 minus the tangent is 0 over 0 cubed. Well, tangent is 0, right is 0. We showed that over here. So we have 0 minus 0, which is 0. And 0 cubed is 0. So we have 0 over 0 form. Okay. So we can apply L'Hopital's rule. So when we differentiate the numerator, the derivative of x with respect to x is 1. The derivative of tangent x is secant squared x. We already know that from over here. And the denominator derivative x cubed with respect to x is 3x squared, using the power rule. Okay. Well, when you do the direct substitution, we have 1 minus secant squared 0 over 3 times 0 squared. And we know from over here, secant 0 squared is equal to 1 squared, which is equal to 1. So the numerator is equal to 1 minus 1. Denominator is equal, right, 0 squared times 3 is 0. And so we have 0 over 0 form in evaluating this limit. So we can apply L'Hopital's rule again. Okay? Well, differentiating the numerator gets a little tricky here, right? Derivative of 1 is 0. But this, now we're going to differentiate secant x squared. And that's the same as secant x quantity squared, right? So when we have the minus sign out here. So we have to use the general power rule, right? You bring the 2 down in front of secant x. Subtract 1 from the exponent, which is just 1. So we have minus 2 times secant x to the first power. And now we got to multiply that by the derivative of secant x. What's the derivative of secant x? Secant tangent. So we have secant x times tangent x all over the derivative of 3x squared, which is 6x. So, clean this up a little bit. Two and 6 are both divisible by 2, right? So 2 cancels, 6, right? Divide 2 by 2, you get 1. Divide 6 by 2, you get 3. And then you have secant x times secant x, which is secant squared x. Times tangent x. All over 3x. Right? 2 divided by 2 is 1, 6 divided by 2 is 3. Okay. Now, you know with limits, you can bring a multiplicative constant out from the limit, right? So I can bring, so this is the minus 1 over 3. So this is equal to minus 1, or minus 1/3, excuse me, times the limit as x approaches 0. Okay. Now, we got minus 1 over 3, and now I have, I can split secant x squared times tangent x over x. I can rewrite that quotient as secant squared x over 1 times tangent x over x, right? I can write the quotient secant x squared times tangent x over x as a product of 2 quotients. Okay? Well, as x approaches 0, secant x squared, right, over 1 approaches secant 0 squared. And secant 0 squared is equal to 1. And as x approaches 0, tangent x over x approaches, I erased it, didn't I? No. Tangent x over x approaches 1. Right? So this secant squared x goes to 1, and tangent x over x goes to 1. Okay? We showed that already over here. Okay? As x approaches 0, the secant x squared, right, it goes to 1. And as x approaches 0, tangent x over x goes to 1. So this limit, right, up here is equal to minus 1/3 times 1 times 1, which is equal to minus 1/3. And now you have everything you need to successfully complete the WebAssign homework due Monday night. Okay? So have a good day. I'll see you tomorrow.
Thank you.